All right. So tonight we'll be doing English again, just for fun. And also because I tweeted in English that I'll be streaming, so in case people who don't speak German saw the tweet and are joining, I will stick to English. Hi, Thorsten. All right. So tonight I'll be streaming in English just because I tweeted in English, so I don't know. Should people join who don't know German so they are not disappointed? But I don't know if the tags are actually correct that I used. I think I changed them to English. I don't know if Twitch actually saved that. All right. Anyway, let's get to the meat of tonight's show. So, over the past weeks, we have worked on this on our tool called MetaCG, which you can find on GitHub. It's open source. However, the particular branch that I'm working on is still a private working copy. But it's as soon as it's merged, we'll push to GitHub. And tonight we'll be doing two things. One is we will add a feature that will count for every function how many distinct types are used within that function. And then for the main function, we're actually going to add the totals for the whole program so that whenever you query the main function, you actually know how many types are used across the whole program. We do that because we're kind of interested in just seeing like how many different types are used within some of the target, the scientific codes that we're looking at. And also it's a neat like little thing to do in a Clang tool, so in a compiler-based analysis tool. And so I figured that it makes sense to have that here. And we should be able to actually implement that within not too long. So then obviously we want to add some tests. And then second for tonight is fixing some more of the already existing tests, because we are currently having the pipeline fail for a couple of our integration tests, which is because I introduced a new file format, and for that I did not change yet all the integration tests. So we're going to continue on that, and my hopes would be that by the end of tonight everything passes and we can actually merge this feature branch into Devil, and then it's public on GitHub. All right, so let's do the fun part first and then go to the tests. Are we going a little like back and forth? All right, let's see. So what we in the software architecture of MetaCG, we build a call graph, which is just a graph that shows which functions potentially call which other functions. And then after that, we have this notion of a meta collector, which is invoked on a single function. As one can see here, we have this calculate for function decl method that is given a function declaration, and then we can inspect the function using the Clang tooling API. So what we're going to do is we are going to implement a new meta collector. And we're going to call it type collector, or type, maybe let's have it unique type collector. Because we are actually collecting the unique types, right? So, and then we have this calculate for function decl that we are overriding, and we are going to implement that. And then just add the constructor. Hi, Roman. Yeah, so tonight I'll be sticking to English because I tweeted in English that I'm going to be live, so I don't know. Should people join? They are not, like, irritated. All right, so this is the collector, and then we also need to have the data container, which is this meta information. And we usually use it just with a little struct here because it's like a pod anyway. So let's say unique type information. And that is, I think it's a meta information, yeah. So to reiterate on that, so what we're going to do is we're going to have a little a pass in our call graph construction tool that simply computes how many different unique types are used in the different functions in our program. And for the main function, we are adding the overall sum of the different types so that we know how many types are actually used in the program. And yeah, so then so the unique type information, that is basically what is our data container that we calculate for each function. And so what we can do here is, let's say we have we could simply have it as a integer for the num types. And then this is the apply on JSON is basically what exports the data container into the JSON file that we are creating. And so we are overriding this one, and then we are only exporting that if the format version of the JSON is larger than 1. So we are at least using file format version 2, which has a different structure to it for a better organization of such meta information. Okay. And so here we are going to have basically two different things that we are collecting, because we are collecting the function local stuff, and we are going to calculate the collecting the global sum of this of these things. So we are having a stud set here with Clang type pointers. God, I can't type. This will be the set where we collect all the unique types across the whole program, and then for every function we are having also a set oh boy, finally. We are having a set of unique types for that function. Okay, and so my idea or the background is that we are inserting the type of every variable that is referenced, so that we have like the used types, right? And so, I mean, obviously across two functions we may like count types twice or like multiple times, right? Depending on how many functions we have. But then we have this global type set where we just like put everything into it, and then because of the set properties, we are having the total number of distinct types used in the program. Okay, anyway, so what we are actually interested in here, and I'm talking about variable types, not like function types and stuff, right? So something that might be quite handy to have is a way to just go over all the what is called declaration reference expressions, or declaref expers. And let's just see what I mean with that. Oops. So if we look at the, let me just set up another alias here. So that we can inspect the AST a little easier here. Okay, that's pretty. Okay, anyway, so if we here, okay. Oh. Okay, finally. So if we look at that, then we have a declaref expr, which means that we actually access a variable, right? For example, the I. So we have a var decl I, and then we reference a declaration. We reference a declaration. So we're referencing the variable I, and with that we can query which type that declaration has that we're referencing. And so that was the basically the way I thought of going through all the declaref exprs that we have in the program and then collecting the type information. Because then we can exclude the stuff that is not used. And to do that, what we are going to do is we're going to use a visitor which is a traversal mechanism for the AST provided by the Clang tooling API. And in particular, we are going to use a statement visitor. And we are doing that mainly so I can like copy paste what I wrote a couple of times now. No, it's more like, so the statement visitor makes sure that we can actually visit every statement node in the AST hierarchy. And as such, the declaref expr is a statement in the Clang hierarchy because it actually inherits from expression, which inherits from statement. And so we can implement only very few functions, which mainly is like the visit statement. Oh, okay. Guess I screwed that one up. But anyway, boy. Okay, so we're going to use the statement visitor, and then we have the visit statement, which for a generic statement, it simply iterates over all the children. And if the specific child node is not a null pointer, it calls the visit method on it. And now we are interested in the decoref expers, so we are overriding the visit decoref exper method, or in this, in this particular case, we're not necessarily overriding it in the traditional way, because the Clang visitors are not the visitor pattern that rely on virtual dispatch, but instead they use the what is called the curiously reoccurring template pattern, if I'm not mistaken here, which can be seen with that we're injecting the specific class as a template parameter into the parent class. And so we will simply cast the this pointer to the more derived type when calling functions. So we're not like relying on virtual functions here, but as soon as we implement that in our derived class, we will make sure that we actually dispatch to this one and not to the parent one. Okay, anyway. So now the let me get this out of the way for a second. Okay, so now that we are here, we can see that if we have a we can cast the, or we can get the let's just do it like this. We get the decal, and if that is a null pointer, we simply return, because then we cannot figure out anything anyway. But if we apparently can get the decal, then we are retrieving it. And we can get the type. And the type should be a qual type, which is a layer in between, such that you can have, for example, a const int. Const in that sense is the qualifier, so it's a qual type, right? So type is int, but the qual type would be const int. And so ty will be a qual type here. But we can also get the type pointer. And that would give us the actual type pointer from Clang. Now let's have a CTOR that gets a stud set const Clang type pointer ref func types. And then we have a stud set of const Clang, type pointer ref f types. And we initialize that here. And now Here we say f-type insert I. And for very easy cases, this would actually already be it. But we'll look into a little more interesting cases in a second. Anyway, so we have a decrefexpr visitor. And we want to make sure that the function we are processing actually has a body, so has a definition. And so if that is not the case, then we are going to return a std make unique how did I call that? Unique type information. Right? And so if we have a body, we can create our decrefexpr visitor and then visit the decal get body. Oh, it's obviously not a pointer, so we're using the dot instead of the arrow expression. All right, so now we're visiting that, and during the visit we fill the function local and I have a typo here. That should be the unique types set, because the unique types are the function local set. And then when that is done, we do a we again create a unique type information. And have the num types be unique types size, which simply gives us the number of different type pointers that we got from the visitor. We also have a global types insert std begin from unique types and std end from unique types. So we are inserting all the function local types that we found into the global set, because again, because of the set properties, we are not counting types twice here, because the type pointers are actually unique in the Clang world, as far as I know. Should be. Otherwise, if you have like two different int types, that would probably get you some trouble. Eventually, anyway, we're going to return the unique type information, unique pointer. By the way, if you have any questions, feel free to like jump in the chat. and ask them. I'm happy to try to answer and address questions. All right. And so, well, let's see if that actually compiles. I do tend to have typos, so let's see how many I introduced here. Okay, so far that looks actually better than I expected, to be honest. Nice. Which would... oh, there we go. Yeah, right. Okay, it's not a typo, but a stupid error. For our for some of our testing, I actually added a equals method for the meta information, so we can compare. We have a like file property, or I mean, in quotes, like file property. It basically just tells you where it comes from and whether that is a system directory or not. But so we have file paths as meta information. Now, if we do our testing, we don't know the actual path of stuff because of we're not currently running in a container in our testing, but that's a whole different story anyway. But so we had to make sure that we don't compare, just string compare the whole path, but instead we would actually only get the file name of that property instead of the whole path, so we can compare the file name in case we like if case like something goes really wrong, and so our tests actually catch that. However, the whole path should not be part of the testing and the assert statement basically. So that is why we introduced this equals method. But now obviously you also have to implement it for all the other parts, because otherwise they will be pure abstract. And now simply returning false is not the way to implement these things, I know, but let's see if things compile. And if they do, then we can like implement this correctly and then add tests to actually make sure that we're not blowing things up here. All right. Let's see. Oh, I forgot. I can actually, let's see. We are compiling, right? So let's have the correct XKCD for that purpose. All right. We should be done by now, so there we go. All right. Okay, so now we need to implement how we export this thing into the actual file that we are creating, where we store the information. And here what we do is we typically just say that so the file format has for every function this meta field, and then we export the oh, we also have to give this thing a meta field name, if I recall correctly, at some point. Oh no, it's from the, yeah, okay, anyway, never mind, I was wrong. And then this simply is the num types integer, right? Which brings me here. Now, if we I said that we are going to attach the number of global types to the main function. So if decal, which is the function decal that we're currently processing, is main, then we are actually saying that UTI num types would be global types.size, right? Now, one of the problems here that we currently run into is if we have multiple translation units that we're going to process, we are not going to correctly compute the number of types in the whole program, because we will only compute the number of types used in the single translation unit in which main is defined. To fix that, we would also need to have a string representation for every single type, then unparse this into a set of types of these string representations, and then in the step where we merge all the different information from the different translation units, we would then create a one single set in which we insert all the different type strings, and then use that size as the overall type size. But for now, let's consider we have one single translation unit because we're only concerned with one for now. Just to make this work, and then we'll continue from that. All right. Hi there. Yeah, so just to rebroadcast that information, tonight I'll be streaming in English, Yeah, because so I announced it on Twitter in English, so um I was thinking of like if people who are not familiar in German with German should join, so they're not irritated, I will simply do English. Um, I mean, I guess that's probably not the case anyway, but you know, don't set expectations that you don't meet, and so let's do English for now. Let's do. I probably switch back and forth at some point with like Wednesdays, uh, like the evens in English, the odds in German or something. I don't know, or just how I feel. Anyway, so we have implemented our visitor, so we can find the different type pointers in a translation unit. We count them by simply putting them into a set, and then we add this information to the CG. Let's just compile this one more time and see if I made a stupid mistake. All right. Let's see. Well, so this project is actually, I think it's going well. At least it solves let's say it solves the current challenges that we're facing, that we're interested in. I mean, there's obviously more to do. Um, for the particular project where this is also used, which is the Pura profiler, we could move a little faster. But it's also mainly me working on it, so it's you know, uh, yeah, it just takes some time. Anyway, so let's see what happens if we simply run the CG collector on one of the test files. And if I would use the correct flags, we may even get the correct answer. Oh, what did you find out about Clang and GCC? Some difference or some unexpected commonality? No. Okay. The final step, I actually forgot. So we obviously need to register the collector. And we could probably have made that into the code statistics collector. Let's see. Oh, that's interesting. So GCC does actually not respect the order on the stack when you allocate variables. So it simply reorders, or it not necessarily simply, but do you know whether they actually reorder in the sense that they, I don't know, better respect alignment or something like that, or is it just like randomly reordered? So for the moment we will simply have another collector here that we're adding to the. Oh, it's backwards. Okay. That's, I mean, that's sort of interesting just from. Yeah, I wonder whether this is like if they have a declaration stack in their implementation, so they simply like push which declarations they see, and then in CodeGen they simply go from top to bottom and then pop 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 pop. So um, you know, instead of having a list of declarations, having a stack. I don't know what would be the benefit from that though, but it's definitely something interesting. Do you which GCC version, by the way? The current one or? Okay, so apparently I'm doing something wrong. And I guess I did not specify a. No, I did. Okay, so basically the current versions of GCC and Clang. Cool. That's neat to know. Now, may I ask, in like, which sort of field are you working in, or like playing around with this stuff? Is this like work related or just as a hobby, as a sidekick? Oh, okay. OS1 tutor. I don't recall if we looked into these things at that detail in our like basic operating systems course. Like that's obviously also some time ago by now. Ah, I see. I see. Well, Roman, I mean, it's um let's say, I mean, I guess many of the open source folks are uh, also working on these things because they are working on these things as their job. But I mean, some of the open source world is really just a hobby. You know, some people just get are interested in like, oh, how does like how does this work? But I mean, I do see the point, and I do also agree that fiddling around with GCC and Clang is not necessarily what I would expect people to have as a hobby. Anyway, um, oh, okay, that's that explains a lot. I mean, CMake is somehow broken. I definitely agree with that. Just in general. And it's still, I mean, I guess it's still the best we have, but I also think CMake is broken. Oh, yeah, linker errors are the worst. I mean, compiler errors are not necessarily most telling, but linker errors are really just, oh, I don't know where, like, I don't, I don't have a definition for this symbol. Done, right? Yeah, that's. I think linker errors are the worst. Now, there we go. Finally. All right. So let's see. So we already see that something doesn't work. Right? Because main should obviously be greater or equal to all the other functions with respect to the unique type number, right? So if foo has a unique type of 1, main should have a unique type of at least 1. If that makes sense. Sorry, I guess I did not mention that. So today what we are going to do is we are going to add a feature that simply counts how many different distinct types are used in a program. So for example, if you have a variable int I and a variable double d, then you would use 2 distinct types. That's really, I think it's a fun exercise just to play around a little more with the Clang tooling API, and it gives you, it's just a neat metric that you can look at if you're going to inspect a target program. And for example, if you would extract some parts of the target program into a slice, you can actually, or you may be able to use it as a yes, and int x and int y would be one type. But you can use to quantify a reduction in complexity to some extent if you would only consider certain subparts of the program, if that reduces the number of types that you are referencing in that particular subpart. Right. So if you think of it, well, if you have, the compiler would deduce auto. So it would actually come to a conclusion what auto would mean in this particular case. But that's a good point. I don't think we have test cases for auto here. Let's just add a. I actually enjoy auto. I think it's one of the best additions to C++. Mainly because of, you know, working with templates or larger. Yeah, see, people can disagree on stuff. I simply prefer not to type a type name multiple times if the compiler can deduce it. And some of the type names can be a little long. I do totally understand this problem that, you know, like, what the hell is this returning? What am I dealing with here? I mean, that's the problem with, or that I also have this problem with dynamically typed languages. And so I totally see the point. But it's still, if That kind of rings a bell, but so I don't know exactly what it is, but I think I heard the term. I might even have an open tab about that in one of the browser instances. Now here is the point with working with a compiler instead of working at the text level. So I'm using auto here. Oops. There we go. So I'm using auto as the type specifier for the variable I, and then I call foo, and foo returns int, right? Now, looking at the AST, I have a decal statement with a var decal named I, and its type is int, because the compiler actually deduces auto to the actual type. And so the analysis at the AST level sees int as the type and not auto, because auto isn't a type, right? It simply says, please compiler, fill in the blank. And so that's one of the good parts with working at the AST level, where the compiler actually already did all the processing and type deduction and semantic analysis or context analysis. No, contextual analysis, right? Anyway, so that, it knows the program is syntactically and contextually correct. I think that's the best way to name it. Yeah, no, so as I said, I'm a big fan of auto, as you may see from the code that I'm currently looking at, where so for example here I don't want to spell out std unique ptr unique type information, because I think it's just nonsense to type that twice. Or also here, you know that this will be a Clang decal pointer. And so, or in particular, it will now be a const Clang decal pointer. IDEs actually do that by now. So at least kdevelop and CLion do that. For most of the code that I have seen so far. It's a little harder if, like it's very, very templated and you have many, many instantiations of that. And it can be a little slower, but they should typically be able to figure this out. Well, not necessarily. I mean, so the compiler still needs to be able to figure out which type is bound at some at some point. It's more that you usually use auto for, let's say, templated stuff. So if you have like a stud map of something to something and you iterate over that, then you would, for example, use structured binding where you can actually have a const auto pair of key and value, right? Let me see if I. So here, for example, right? Look at this line. So allocs allocs is a stud unordered mapping from stud string to stud string. So here what you do is actually you get a const auto ref of key and value. So you get a const stud pair ref with pair being the value type of stud string and stud string. So if the compiler deduces auto, the type that your IDE may display here might not be the most readable one, depending on whatever, like this type actually is. Because it might just display this as stud unordered map, stud string, colon, colon, value type. Or even more convoluted stuff like GCC would output on the command line when it throws in an error with these types. So your IDE, if it runs a fully fledged compiler to display code hints and like auto completion and stuff, right? It should always be able to deduce the type. However, it might not help you that much to know what particular instantiation of whatever template this is. And you would, obviously you would need to have it at least compiled once, so you have the compile commands, you know exactly how it's actually compiled again, so that the compiler can actually do all this stuff. If you simply go to GitHub and like search the source code of some project because you thought like, oh, maybe I should look at something with a lot of auto, you do not necessarily have a good chance to find out what's going on. Yeah, and if you have, so my opinion with this like auto I equals something with like commas and pluses and function calls and everything, I wonder whether it makes sense to just refactor it so it becomes more readable in the first place. And I don't think that's a problem of the auto keyword, but it's more a problem of like how the code is written. I mean, what might limit the type deduction in IDEs, like with on mouse over, would be the time required to actually generate the deducted type, the deduced type, because it would actually need to basically compile the source or store a snapshot of it somewhere, but that would be get invalidated every time you change something, in particular with templates, right? If you have dependent names and stuff, then it's, I guess that's then again, that's like the corner cases that may pop up here and there. But if you would give it enough time and CPU power and memory, well, yeah, I guess that's your fault. I mean, I feel almost like a relic using Vim with some plugins, and Roman and I had discussions about that. Like what is the actual benefit of using a fully fledged IDE? And um, I think these are the particular cases where an IDE really, really helps, and where like uh, my main problem with IDEs for C++ is basically just setting things up so that I'm happy with how it works. And it just like feels like it takes so much time to actually come up with a nice setup that I like frequently go back to this VI setup that is basically stored in a GitHub repository. Yeah, so my VI configuration is on github.com/jplayer. You can use it as a starting point if you want. Then you see the plugins that I'm using as well. So here, for example, the autocompletion is brought with You Complete Me, which uses Clang. I think it has experimental support for Clang D, but I'm not sure. I know that this question was going to come. Oh, overall, how long it took me to set up VI? I guess I cannot really estimate, but let's just say 2 days. But over the course of like multiple years. And here's the point. With an IDE, if you don't set it up properly, you don't get anything out of it but a very, very slow text editor. With VI, I mean, you have a text editor. It's not slow. It's pretty fast. Like you can use it over SSH and everything. And I can still, I mean, independent of my setup, I can usually just say like, oh, I want to make stuff, right? So I think it's hard to compare these things. Actually, the debugger is the only reason why I would really want to use a good IDE. But there are just not many, well, C++ IDE debuggers out there. I guess that's the problem. Yeah, Roman, I think that, or so with C line, you have, in my experience, which is a little like a little ago, but which was the same for Qt Creator, Eclipse, and whatnot. You actually have to set up the projects, and it's not about setting up like key bindings or your favorite color scheme, right? It's about setting up the project. And I had the impression that like just finding out which compiler is actually used, which toolchain is used, where it actually looks for all the binaries. How do I how do I change the library path that the IDE goes through and searches? How do I set this variable, this environment variable, this stuff and that stuff? And I have to do this for every project. And that is what sort of just annoyed me. So we'd have this for like every single thing you do. But again, I mean, as I said, times may have changed. I just don't know whether I will be looking into things before September 3rd. Um, but after that, I surely will look into uh, I will surely look into C line or even Kdevelop again. Once I've defended my PhD, because I really would enjoy using an up to date IDE with all these nice features that it may bring. Um, I would be so lost to just configure something for Java. I don't know how long it has been to simply like look into this universe. I would probably just call Roman then and ask for help. All right, let's just do some text debugging here in the meantime, because I'm just curious if the processing order isn't the one that I would expect. In which case, it would make sense that there's a that main says it has 0 types and foo says it has 1 type. I mean documentation for the stuff that I'm working on is generally not available, or it's wrong. That's my typical experience. Oh, the processing order apparently isn't guaranteed, huh? Okay, so that's not necessarily what I expected, to be honest. But I have an idea why that is. No, okay. Yeah, that's exactly what I was thinking about. But it should be that. Oh, so we get the node from the call graph, and the call graph is what? Okay, so the call graph is probably a set somewhere. Function map. It's a dense map. All right. There we go. I was actually expecting that we're, or I was under, I had the assumption that we are doing these calculations in the visitor, which would give us a determined order. Yeah. So the problem was that the unique type collector was wrong. That it said 0 for main, which would need to be at least 1. Now the reason for that is, so here we see, for example, that we first process main and then we process foo, which would obviously not work if we want to have main to be the sum of all the others. Or not the sum, but like the set of all the others. And that is because the way how we calculate or how we invoke the different meta collectors, where we don't do that while traversing the AST in the visitor, which gives an actual order to it, but instead we are doing this calculate for, and that iterates over the nodes of the call graph, and the call graph is it actually says non-deterministic order because it is a map of pointers to call graph nodes. But let's see if we can find a different way to iterate this thing. Okay, I mean the other version would just be to simply have another vector that simply stores the decals in order of their traversal. Because I think that could be added quite easily. So the usual, let's say, start for these larger visitors pardon me, would be the visit translation unit decal. However, here we simply have visit function decal and visit cxx method decal. So these two are the main implementation or the major like starting points for the call graph construction. So that would be sorry, I'm getting a little tired. So that would be the potential places where we would add the addition of that. What version, yeah. Yeah, okay, let's just, I mean, it's research code anyway, so let's, we just have an in order decals. And if we include the function in the graph, we also, hi, night MT. So Clang decal is the base class of all declarations in the AST. And then you have function declarations, variable declarations, and like tons of other stuff, other declarations. Yeah. So it's one of the three base classes of the Clang AST, which are like decal, statement, and type. And then so for the moment we're just doing it, well, in some way. Let's just put it that way. Hmm. All right. So now node is no longer a pair. But is the actual decal pointer that we can use for the cast here. Now let's see what happens. So it's all about compiling. Oh, and because you asked, so the i3 setup that I'm using is very, 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 very basic. It's really pretty much the out-of-the-box Manjaro i3 setup. It has 2 editions or 3 editions. One is I have a shortcut to or I don't know, I think it's the same shortcut, but I use Opera as the main browser. And so that is different. Then I have a shortcut to open Slack. And I think that's pretty much all the changes that I do to i3. So it's very, very, very simple. Okay, so that seems better now with the order of processing. And now that should also work. And this actually, I think, looks correct. We are currently not counting the types in function signatures. Which I think is fine, because if you don't reference them, they might not be as useful or of interest. However, let's see what happens if we do that with this expression. So the code is a little different now. We have int, we have pointer to int, and we also basically have an array of ints. We have a void pointer. And so I guess malloc has as the unique type collector has a value of 1 here. I guess that's the void star. And then here we have int star. Maybe even also void star. I'm not sure. Let's look at the AST for a second. So remember, we're going through the decoref expers. So we have int, I think we currently did not exclude function types, so we might even have this one. So let's see, in main we have int. Have to see, look for the decoref express. Okay, here's one. That's void star int, that's a function type. Then we have another decoref express, which is int star, which is 2. We already had that function type. We also already had int star. We did so far not have int, so that's 3. And these are the 3 types that we found. Right? So we don't want to count function types, so we have to exclude them. Now that might be something where we can check whether a type is a function type or a pointer to something that is a function type. And so we are simply going to do a little refactoring here as well, move stuff around. Because I think we can use this one. Yes, because int star and int are 2 different types. Okay, so now the question is, where does the Clang type come from? So apparently it's not directly included here. But I mean, this may work. Anyway, so we are including utils.h here as well. In the hopes that okay, let's see if that still compiles. Or if I really broke some include dependency right now. All right. Okay, so it still compiles. Now we can also use the utils here. And as such, we can do resolve to underlying type, which that does is it strips away pointer types. So now actually with that, the int pointer and int would be the same type. However, we are only going to do that to then look at the whether that's a function pointer type or if it's a function type. So then we can exclude this one, but we will keep int pointer and int as two distinct types. And we will simply do it like this, but we'll insert the decal, get type pointer, because with that, oh, that's a very good question whether int pointer and int ref are two distinct types. At least they can be differentiated here with pointer and reference types. That's a good question. That's actually going beyond what I thought about. I mean, the easy answer, no, it's not an error. It's more of how do I want to treat these different things. So if you think about, is it um, from a semantics point of view, right? This is not about like program theory. I don't know if this is any theory, but if you look at a program and you think about, oh, it uses so many types, it's hard to comprehend. Now, if it also uses pointers to those types, does that increase the complexity of the types it uses? Right. So, in that sense, you could argue that even distinguishing int pointer and int is the same is unnecessary because it's both int, right? Um, and so if is int pointer pointer so much more complex than int pointer in the sense that it adds to the numbers of different types. I mean, you can make errors when you're using these things, right? That's for sure, but so the quick fix to this answer is we simply use the strip away type. And I guess that's the reason that there are no types, that nobody is using it anymore. In the sense of like, modern or new software or evolving stuff. Anyway, oops. Auto is not a type. Auto is a keyword to let the compiler do your job. So auto is different potentially from line 1 to line 10. Which, as I said, can make it harder to understand source code. Sure. But it can also be pretty nice when you write like lambdas and don't know or don't want to type out the specific type that you're passing. Yep. We actually use that syntax in some of the parts. But only for lambdas, not for functions. Yeah, usually you would I don't know if you can do auto foo auto, but you can actually do foo auto uh, and then have the arrow auto. Let me see if I can. Is it here where we use that? Let me see. Yeah, so we do this with lambdas. Well, I mean, obviously auto here is the type of the lambda, but then we have auto as the parameter. We don't specify a return type at all. And then, yeah, so as I said, I do like the auto keyword. I mean, software design doesn't necessarily say that you can read it, does it? It says low coupling and low cyclomatic complexity and whatnot. In that sense, you can argue that if you have a very, very well designed open object oriented program or source base, code base, where everything happens somewhere else, it's also, I mean, it's not easy, for example, to get into the Clang uh, library or how Clang itself works because it's just large and a somewhat complex piece of software. And it uses explicit types most of the time. But you just have to dig through, like, I don't know, a gazillion different classes and things and I mean, large software in itself is just complex. I don't know if that is because of the auto keyword or not. I would argue it's not. It's because of the, like, large and complex system that it is. And the better you get to know it, the easier it becomes to use it, navigate through it, and program for it, in it, with it. And then auto saves you typing. Potentially. I mean, in C++, most definitely. But sure, could be. But I mean, that's like sort of back to the point that Roman also made. If you have IDE support, that certainly helps. And getting into a new project just using a text editor and grep maybe, I would argue that that's not the best, or not say not the best, but that's an approach that is limited in a certain way. If you are, like, if you're fast with the text editor and grep and you can like search everything, and so that's fine because it's the way you are used to work. That's again why I'm using the VI that I'm using. Yeah. I wonder if that is actually, if you run, no, forget what I was thinking. I mean, if it's not there, I guess you can somewhat easily make it. But then obviously it's a research tool that doesn't run on your code base because, obviously your code base uses features that the researcher wasn't aware of or thought were unnecessary or weren't just weren't relevant for the paper. But also, Roman, you know how scarce the landscape for some of the, let's say, useful C++ tooling is, right? Okay, anyway, so based on the question about whether int pointer is the same as int ref, I now have solved this problem by simply saying, oh, we just desugar everything and get to the underlying type so that int pointer and int ref are all the same. And we simply count the types independent of whether it's a pointer to it or a ref to it or it's the type itself. That gives us for the for this example exactly one type, which is int, because we are also just counting the stuff that names refer to, which means that we do not count the void pointer here. Right? Makes sense? Honestly, I don't know if it makes sense, but I also just realized that I forgot to rename the stream correctly. I think this would be the 19th stream ever. Anyway. Okay, so this one should also have ones here. All right, that looks good. I actually guess that all the input codes here would have ones. Oh, now that might be interesting because I think we currently don't handle this correct me. So I know that there at least was a paper that refactored C++11 code back to C++98 code because their use case was from the embedded world where the vendor compiler was still a C++98 compiler, and the vendor was unlikely to move forward supporting C++ in the near future. However, the team wanted to use C++11 features, so they actually wrote a tool that would backport some of the C++11 features to C++98. Or that it would rewrite C++11 features to C++98. But as I said, research paper, probably no tool, nowhere. Oh, for fuck's sake. All right, so there we go. So for this code, we have 0 unique types. Who thinks that this is correct? As I guess no one, and it shouldn't be correct. It's just because how we implemented the visitor. So right now, we simply consider declref exprs. Now, if we look at the AST for this program, we only have var decals with init statements. So we don't have a declref expr that refers to a non-function type thing. So we just don't count anything. So we would need to also add that we visit decal statements. And now I guess that we can oh, we need to Okay, now the deckled statement, this is... For now, we only consider single decals, no decal groups, because decal groups are also a little... Well, in that case, it might even be not too hard. But anyway, so for now, we simply consider single decals and have a C error here. So then we can get the decal and then we can have what? Okay. Let's see if let's look into the Clang documentation. I'll do some zoom here. So I guess we need a value decal to get a type. Or a named decal might suffice, I don't know. Let's see. Nope. Okay, yeah, so let's do get type. Yes, Roman, absolutely. Can you rephrase your question with the auto-ref, auto-pointer, and so on and so forth? So we are casting here to value decal because value decal is the... yeah, then yes. Then the answer is yes. Because as I said, the compiler internally doesn't know of auto. There is no auto in the AST, right? So in the if you look again here at the source code level, we wrote auto I equals foo, right? However, if we look into main and see the var decal of I, there is no auto. It only says int. Because when the compiler parses the source code and does the contextual analysis, it would actually do the type deduction such that the AST contains all type information already. So for example, also during parsing, lambdas would be instantiated, so on and so forth. And so thereafter, everything needs to be fixed. No, auto leaves no room for optimization. Auto really is just telling the compiler, I was lazy, I didn't want to write the type down, please do that for me. All right, and then after we figured out the type of the value decal, we also inserted into the function local types. So I like the thinking of this, but also if you think about, so what would you expect the compiler to do? Change the type from int to short in that sense? But then short might not fit well with hardware alignment conditions, so you again pad it to actually extend to long because that's then better for the word size of the processor. So it's okay. Now let's see what we have. But then you would also need to unpack these things, right? If you actually want to access the actual values. So instead of doing aligned read or aligned load in that sense, you would actually load and then you would need to mask. And then you actually would need to, if you would store it actually in a long, then you might need to shift things around to actually get the correct. So I don't know. But I mean, that would be very machine specific anyway. So it will definitely be much later in the pipeline. Sure, there is a size optimization option. But that usually means that you just simply don't pad. I mean, obviously you do some other tricks there, but anyway, that so the let me say, I usually don't care about the size. Uh, but that's particular to, I guess, an HPC. Nobody cares about the size as long as it's running fast enough. Well, that's not true. So recently I was watching a talk about Cocos. Yeah, embedded, exactly. Embedded is where size matters, but um, now in HPC there are multiple performance portability layers flying around. One of the more let's say mature ones, and that is actually used is Cocos. And Cocos is you would write in Cocos, and then you could say, oh, I want an OpenMP backend, or I want a CUDA backend, or an OpenCL backend, or what have you. Now the problem is Cocos does everything with template magic. Now templates do tend to become a little convoluted if you have large instantiation chains, right? And now they actually had trouble with executable sizes of multiple gigabytes, mainly because of the function identifiers. Because now with C++, you take a long template name, you then mangle it so everything of that template instantiation party actually becomes part of the name that is in your binary. Now you have that for many different instantiations, because obviously you have also optimized, and so you have like specializations for vector length 1, 2, 4, 5, 7, 8, what have you, and then your identifier names actually reach the limits of, for example, or exceed the limits of, for example, what GDB can display. And no, there are no mechanisms to short these names. At least there weren't when the talk was given. They probably now like talk to people, but it's also not something that, you know, like many people run into. And I mean, it's meant to generate, given a specific scheme, generate unique identifiers. So there's also only so much you can do with it. All right, anyway, so let's look at the example again. After we have now implemented the visit decl statement function, we now see that in foo we collect two unique types, which are those two. And then we have one other, which is the int down here. I'm not sure I understand correctly, but then you can only do that for symbols that are not exported, because exported symbols need to be visible from the outside in the very specific name that or way they should be named so that you could call them. I don't know for template instantiations though, how these work. Whether they actually also need to be, whether the symbols need to be exported. And I mean, I won't. Yeah, I don't necessarily know about anything about in JavaScript. Well, export is a default on on Linux, right? You would actually need to mark symbols as no export. At least that's what I recall. I don't know if this is still true or whether this was at all true. Yeah, I think what Roman said is quite true. So like all these symbol stuff is, yeah, I guess it's a little more, I mean, it's a little more complex. I guess you could rename stuff, sure. And this is why I said I don't know about how templates. I don't know if you can actually export templates. But you can certainly, if you have a shared object and you know the exact name of something, you can certainly call it template instantiation. And you can like override it and have then LD open the specific symbol. So this is, you would need to take all these things into consideration. And that is, as Roman said, I guess that's a little harder in C++ for all the different cases on all the different platforms for all the different compilers. And if it's not, so if you don't respect that, then you don't have a compliant compiler anymore. I mean, you can do whatever you want, but you don't have a standard compliant C++ compiler anymore. Right? You can just rename whatever you want, but then you're using C++ as the input language and then produce something. But I also don't know about the exact wording from the standards document on like function identifier generation for the object code or so. Anyway, so with the smaller examples here, I'm now somewhat happy. And I will probably test this on a little more or a little larger code base tomorrow. And then see what happens. And also look into the into the tests that are currently failing tomorrow. Because so we have two different approaches to testing. Ones are the AFL based tests, and the other ones I don't know how they work actually. So okay. Yeah, okay. So that's something I'm not going to do now, because now I think I'll leave it with where we are. And as I said, test the stuff on little larger code bases tomorrow and fix the tests. And thank you for being with me and for the very, very active chat. I really enjoyed that. Specifically in these like Corona times where not too much interaction is going on anyway. I hope that what I did was somewhat entertaining or interesting. Thanks, Roman. That's awesome to read. And I'll be back streaming definitely on Wednesday, but probably also on Sunday. Then potentially German again, but I mean, also I can always switch to English if that is like wanted or preferred. And thanks. So thanks for being here. I'll be back on probably Sunday, definitely Wednesday. More programming. And I hope you stay safe. Take care and good night, everybody.